For the next few classes, we'll be talking about graph algorithms, so let's start by defining some graph terminology. A graph consists of a set of vertices and a set of edges, where each edge indicates a connection between two of the vertices. Broadly speaking, we have two types of graph, which are undirected or directed. In an undirected graph, the edges have no particular direction, and so an edge from 3 to 7 is the same as an edge from 7 to 3. We'll generally still write the edges as ordered pairs for simplicity, but there is no distinction between UV and VU, so a set would be more technically correct. In a directed graph, on the other hand, edges really are ordered pairs because there is a specific direction to the edge. And so, in this graph, we have an edge from 1 to 2, indicated by the arrow, but we don't have an edge from 2 to 1. For many of the things we will use graphs to represent, there is additional data we are interested in besides just the edges and vertices, and so there will often be additional data associated with the vertices or the edges or both. The type of data we'll see most often are numerical values associated with each edge, and we'll call such a graph a weighted graph. And weighted graphs can be either directed or undirected. For each of the graphs I've drawn here, we can specify them precisely by writing out the set of vertices and the set of edges. So when we provide a graph as input to an algorithm, we would need to somehow specify the full set of vertices and the full set of edges. When we analyze the running time of our graph algorithms, we'll think in terms of both the number of vertices and the number of edges, and so we'll define the size of the vertex set to be n and the size of the edge set to be m. And so in this case, we have n equals 7 and m equals 10, while in this case we have n equals 8 and m equals 13. Graphs come up in all kinds of applications in computer science and in many other fields, but here are some of the examples that I find it most helpful to think about. The core representation underlying Facebook can be thought of as an undirected graph, where the vertices are the users and the edges are friend relations. And because both users have to accept a friendship, that relationship is always undirected. On the other hand, to think about Twitter, it makes much more sense to think about a directed graph, because the core relationship between users on Twitter is following, and a following relationship does not have to be mutual. And one of the most classic examples of a weighted graph is a map representing a road network where the vertices are cities and the weights on the edges are the length of the roads connecting those cities. In a moment, we'll start thinking about data structures and algorithms for graphs, and we'll be describing the size and running time in terms of n and m. So before we do, it's worth thinking about the relationship between the number of vertices and the number of edges. And if we think in terms of big O and give an upper bound, we know that the most edges that a graph could possibly have would be when every pair of vertices is connected. In a directed graph, the most possible edges would be for each of the n vertices, we have an outgoing edge to each of the n minus 1 other vertices. So n squared minus n gives us an upper bound on the directed edges. And in an undirected graph, the most possible edges is half as many as in a directed graph, so we get n squared minus n over 2. So in either case, m is big O of n squared, but it's worth remembering that this is only an upper bound, and in many graphs, the number of edges will actually be much smaller than this maximum possible number of edges. There are a number of different data structures we could use to represent graphs, but the primary two are known as an adjacency matrix or an edge list. In an adjacency matrix, we have a two-dimensional array where there are n rows and n columns, one for each of the vertices. And in each cell of the array, we'll have a 1 if there is an edge connecting the vertex for the row to the vertex for the column, and we'll have a 0 in that entry if there is no such edge. In an undirected graph, this matrix has to be symmetrical about the main diagonal, because anytime there is an edge from R to C, that's the same as saying there is an edge from C to R, but any square matrix of 1s and 0s could be a representation of a directed graph. In the edge list representation, we will store n different lists, where each of these lists corresponds to one of the vertices and will contain all of the other vertices where there is an outgoing edge from this vertex. So if we think about the size of each of these data structures, for the adjacency matrix, we need big O of n squared space, because for every pair of vertices, we have a 1 or a 0. For the edge list, we have n different lists, but some of those lists might be much shorter than length n, and so actually the total number of elements in all of the lists is equal to the number of edges, and so we need space equal to the number of nodes to store each list, plus the number of edges to store all of the elements in those lists. From earlier, we know that m is upper bounded by n squared, so at worst, the edge list takes big O of n squared space, like the adjacency matrix, but if our graph is relatively sparse, like the examples we saw before, then m might be closer to n than it is to n squared, and the edge list might require much less space. So why do we have these two representations? Well, they are good at different things. The edge list can be an effective representation if we are doing a lot of operations that involve looking at all of the neighbors of a given vertex. Because if we want to know all of the other vertices that have an edge from a particular vertex, then we just need to scan through the list for that particular vertex. Whereas in the adjacency matrix, we would need to scan across the whole row, and if that vertex didn't have very many neighbors, then scanning the whole row would be an inefficient operation. On the other hand, the adjacency matrix can be an effective representation if the operations that we are doing frequently involve looking for the presence or absence of a particular edge, because it takes constant time to look up whether a particular edge is present here, whereas it might require a linear or log time search through the list in this case. We should also define some terminology for talking about graphs and their components. We call vertices that have an edge between them adjacent, and this is the source of the name adjacency matrix for the data structure. A path is a sequence of vertices where each vertex is adjacent to the next. And sequences of vertices could contain repeats, but if there are no repeats in a path, then it's a simple path. And if a path has the same first and last vertex, then it's a cycle. We'll define two vertices to be connected if there is some path from one to the other. I will often slip up and use connected when I really mean adjacent, but please correct me if I do this. And then the connected component of a vertex is the set of all vertices that have paths from that vertex. Of note, these ideas of connected and connected component would be different in directed graphs or undirected graphs. And so these definitions I've given here apply specifically to undirected graphs, and we will talk about the analogous definitions for directed graphs later. Finally today, I'd like to give you pseudocode for a graph traversal algorithm, which will let us investigate paths, cycles, connected components, and more. And as we'll see, this basic traversal pseudocode has many variations that can give rise to breadth first search, depth first search, Dijkstra's algorithm, and more. Our traversal algorithm takes a graph and a starting vertex, and it will explore all of the vertices that can be reached by starting at S and following edges. This algorithm works by maintaining a frontier, which holds all of the vertices that we have not yet visited, but that are adjacent to some vertex we have visited. And in each iteration of its loop, it will take one vertex from the frontier, and then look at all of the other vertices that are adjacent to that vertex. And for each of those neighbors, if we haven't visited them before, we will add them to the frontier. So the goal of this algorithm is to eventually visit all of the vertices that we can get to by traversing edges starting from S. But the order in which we visit the vertices will depend on how we perform the remove from frontier operation. We will see lots of variations on this core algorithm, but the main variations to consider are that if we organize the frontier as a queue data structure, where the first vertex we put in is the first vertex we get out, then we will explore the vertices in a breadth-first search order. On the other hand, if we organize the frontier as a stack, where the last vertex that we put in is the first vertex we get out, then we will explore the vertices in a depth-first search order. Or if we organize the frontier as a priority queue, where the priority is the total path cost, then we get Dijkstra's algorithm for finding shortest paths on a weighted graph. For many of the algorithms that we see in this class, we will create modifications by giving them different inputs. But for our traversal algorithm, we will create lots of variations by slightly modifying the pseudocode. In addition to the different orders of traversal, sometimes it might make sense to change when we mark things as visited. For example, instead of marking V as visited when we take it out of the frontier, we could mark N as visited when we put it into the frontier. And this could make the algorithm more or less efficient in certain circumstances. The downside of the various ways that we will modify this algorithm is that for each of those modifications, we will need to reason carefully about whether our correctness proofs still apply under the modified versions of the algorithm. We'll spend lots of time in class and in future lecture videos on correctness of variations on our traversal algorithm. But for now, let's take a moment to think about its running time. For many of these steps in this algorithm, their efficiency depends very much on what data structures we choose to represent the graph, or the frontier, or the visited set. But let's for a moment assume that we are using a first in, first out queue for breadth-first search as our frontier. There are various ways, including linked lists, that we could implement a queue where both adding to the end and removing from the front are order 1 operations, and so both initializing and removing from the frontier can be big O of 1. Of note, however, if we use a priority queue for the frontier, where the underlying data structure is a heap, we might end up with log time operations. To represent the set of nodes that we have visited, the simplest thing we could do would be to make a list with length equal to the number of vertices, where we initialize all of the elements to be 0, and then each time we visit a vertex, we can just switch that element to 1. That would make the initialization a linear time operation, but marking a node as visited would be constant. And likewise, checking whether something has been visited and adding something to the frontier are order 1 operations. So far, most of our operations are constant time, but many of them happen inside this double loop, and so we need to think about how many times would this execute. Well, a first guess at the running time might say that when we loop through the neighbors, there are up to n-1 neighbors. So this could take linear time, and on each iteration of the while loop, we will remove a vertex from the frontier, and we might have to traverse all of the vertices in the graph, worst case. So we would also have big O of n iterations of the outer loop, and if our inner loop runs big O of n times for each of big O of n iterations of the outer loop, then overall our while loop would take big O of n squared. And that would give us a valid upper bound for the running time of this algorithm. But as it turns out, we can do better. In class, we will look into a more careful analysis of how much work could be performed in this while loop in total, and we'll come up with a bound on the running time of our traversal algorithm that is better than big O of n squared.